Welcome, everyone. Welcome, San Diego. My name is Mohammed, and this is my colleague Elham. And we're here to welcome you to the first tutorial of the morning. And we're going to talk of the day. We're going to talk about FPGA applications on Nautilus. So we're going to, first of all, you can find the slides on GitHub. We also have a small notebook to show you the steps we're going to take in launching a very simple experiment on FPGAs. But if you would like to follow the slides on your own computers, you can find the slides at github.com/nrp-nautilus/6nrp-fpga. And I'm going to give everybody a minute to get it down. All right. To get started, first of all, let's talk about FPGAs. So FPGAs, I know a lot of people have always been intrigued by FPGAs, especially for Nautilus users. A lot of Nautilus users know that we have FPGAs, recognize that they are a hardware resource, but are not very familiar with them, their capabilities, what they're capable of, their use cases, why we have FPGAs, and most importantly, how to use them. So when we say FPGAs to define what they are, in the simplest of terms, they are chips. So they are programmable chips. FPGA is short for field programmable gate array. Field programmable means that is, as the name suggests, it's programmable in the field, as in after deployment, after production. Once you have the card installed, it is programmable. You can reprogram it to do whatever specific tasks you want to do. Gate array, as in it's an array or a grid of logic gates. So it is fully programmable hardware that you can write software to program to optimize the pipelines to do whatever sort of compute or acceleration you're trying to do. So those chips come, specifically the ones on Nautilus, and some of them are embedded, but in the context of the FPGAs on Nautilus, we're talking about PCIe cards. They're installed on the nodes, on the host servers, and they're acceleration cards that can be, in theory and practice, be programmed to do any sort of task. And this is where the analogy comes from, that CPUs, CPUs and GPUs, they're like a Swiss Army knife. Whatever you throw at them, they're the compute. Each one of us has a computer in front of them, it has a CPU, it's processing whatever's getting thrown at it. On the other hand, what are FPGAs? FPGAs are like custom-built machinery. So they're hardware that is designed to do the same specific tasks with high throughput and low latency. By high throughput, we mean processing high volumes of the compute of the data. Low latency means the cycle time in doing each computation is low in nanoseconds. And of course, they're energy efficient in terms of wattage and their power consumption, and they're flexible. So they're fully reprogrammable, and which is what makes them custom rebuilt heavy machinery. So heavy machinery is built to do the tasks. Here, they are fully programmable cards. I don't know if anybody here is familiar with the ASICs, which are application-specific integrated circuits. The ASICs are circuits that are designed to do specific tasks. One main example is Tofino chips on switches. Those Tofino chips are P4 programmable. They're designed to do packet processing in a way, in an optimized way. FPGAs, on the other hand, offer sort of an upside here in them being completely programmable in terms of hardware design and hardware description. So how does that translate to the real world? We got down to how can we use them? How are FPGAs really programmable? We have the cards, we're using them, we provisioned them on Kubernetes, we have the cards. How are they programmable? Well, there are two main pipelines or two main approaches to programming FPGAs. The first one is hardware description language. And it's the main approach. It's how FPGAs are actually programmed. And it's very low level languages like Verilog and VHDL, if anybody's familiar with them. With those languages, it's going to get very technically challenging to program the FPGAs, because you're getting down to the low level of each circuit behavior and logic gates. And basically, if you want to do something simple, like use the FPGAs as smart NICs, you want to process packets, just for example, do a simple network application that does, for example, segment routing. You don't want to get down to actually designing the circuit by hand, wire by wire, and optimizing clock cycles and having it fail most of the time, and get down into that whole approach. Because most people who want to use FPGAs come from very different scientific domains, and most people that can use them and put them onto research are not necessarily FPGA designers and hardware designers and FPGA engineers. They just want to get their workloads done on FPGAs, and that's where the more lovable approach comes in, which is the high-level synthesis. So high-level synthesis means using higher-level languages, which like C and C++. And in this context, C is a high-level language because it's much more high-level than writing Verilog, for example. You can basically write your C++ program and throw it onto a compiler. It's essentially a compiler that takes your HLS C++ code, and it does the synthesis onto Verilog and turns it into a bit stream. So bit stream is the logic that gets loaded onto the FPGAs. So Verilog is turned into bit stream. With HLS, you have another level on top of it. You have your HLS code. It gets compiled into Verilog, and then that Verilog gets loaded onto the FPGAs. So this is just a brief example. On some FPGAs, this is what a simple hello world might look like. To actually get it to work on the FPGAs and not fail at all, you might end up writing all of this just to get a hello world. On the other hand, it's like 5 lines in C++. So this is just to demonstrate why HLS offers advantages. So now we're going to talk about the FPGAs that are on Nautilus, on the National Research Platform's Kubernetes cluster. So we have the AMD or Xilinx, after AMD bought Xilinx, they're called the AMD Alveo U55C data center cards. So this is what they look like. And their form factor is half length. So they're much smaller than a normal GPU. If you look at them, they're like this big. If anybody's familiar with the U280 FPGAs, they're twice as big. The U55C FPGAs offer 2 main hardware specs that are very favorable in programmability. Is that they have 200 gigs per second Ethernet connectors. And I'm saying Ethernet connectors, but since FPGAs are fully programmable, it doesn't have to be in Ethernet. You can program them to do InfiniBand. You can program them to do your own protocols because they're everything after layer 1, you're programming it however you want to, however you see fit. And the other thing is they have Gen 3 PCIe that offers bandwidth, so you can, how you communicate with the cards. The cards are installed on the host server, and the host interacts with the cards through the PCIe and through the Ethernet. The Ethernet is connected in Nautilus, the U55C FPGAs. They're connected to a Tofino switch. So we have 32 of these cards. All 32 are connected to a Tofino switch right here in SDSC. And it's an edge core for 100 gig. The Tofino switch itself is P4 programmable. And these cards are also P4 programmable and P4 capable. You can see here what sort of bandwidth for SRAM we're talking about. Talking the order of terabytes per second. And for HBM, high bandwidth memory, we're also talking 460 gigs per second in bandwidth. And the advantage of these cards over other Alveo models is that they offer more HBM memory, which makes them suitable for all sorts of applications, including any sort of science domain acceleration applications, like genomics, including network applications as well, whether they're research network applications or deployment network applications. And to get more about use cases, so the biggest thing right now, what everybody's talking about is machine learning and artificial intelligence. And since the cards are programmable, so in theory and in practice, they are built to do whatever workflow we want. They are capable of running neural networks. And that's where Vitis AI comes in. So Vitis is software that is provided by AMD, or before it was called Xilinx. Vitis AI is a tool that allows loading neural networks straight from TensorFlow and PyTorch straight onto the FPGAs for the Alveo Versal FPGAs, both for inference and fine-tuning and for all sorts of applications. it can load transformers just fine, and it offers a very simple pipeline where you have your model in Python just loaded with one tool, and it's on the FPGA. And more importantly, so this is a commercial product. This is provided by AMD, but more importantly, there's HLS for ML. HLS for ML is completely open source. It's a project by FastML. It converts machine learning models onto FPGA-ready HLS designs. So takes the models, turns them into HLS, compiles them to Verilog, and loads them on the card. But it is fully open source, and it's academic and free and available and supported on Nautilus. And it's what Elham is going to talk about and show you and walk you through a tutorial on using HLS for ML to load a neural network onto the U55C FPGAs. The other use case I want to talk about is those FPGAs can act as smart NICs. Like we mentioned, they're fully P4 programmable, which means you can use them for your deployment network, for your network research. You can load, for those of you who are not familiar with P4, so P4 is it's a C-style packet processing language. It allows you to write very simple, very easy to use pipelines for packet processing. And we have the tools already deployed on the cluster that offer a pipeline. So it's as easy as plug and play. You can write your P4, and we have all the tools ready, all the documentation will lead to it, and we're going to talk about it more at the programmable networks tutorial. We have all the tools that let you write your P4, load it onto the FPGAs, test it, simulate its behavior, and deploy it on the cards. You can send traffic through the 100 gig connections, and you can send traffic also through DPDK. You can also use the PCIe connection to send traffic from and to the FPGAs, between the FPGAs and the host and the FPGAs and the network, since those FPGAs are on the switch that is connected to the internet. So they can be used on all sorts of topologies, all sorts of network research. So FPGAs on Nautilus. Like we said, so this is a map of all the Nautilus sites, NRP sites. You can see here, if you zoom in here, so this is San Diego, this is where we are, this is La Jolla. Right here in this building, this is where we have all 32 U55C FPGAs right here in some room, I want to say on the first floor. And this is somewhat what our topology looks like. So these are the nodes that host the FPGAs. And like we mentioned, this is an edge core switch. All 32 of them are connected to the switch. The FPGAs, all of them are programmed and ready to use. The ones that are highlighted in green, the interesting thing about them is that all of these FPGAs are not physically on these hosts. They're composable FPGAs. They're on Fabrics nodes and GigaIO fabrics, and they're composed onto these nodes. And so these cards exist physically on the nodes. The nodes are the host servers are Kubernetes nodes. Those nodes have a device plugin running, the Xilinx device plugin. It broadcasts and displays the cards for Kubernetes. So they're available as a resource. If you go onto the portal, the Nautilus portal, the portal.nrp-nautilus.io/resources, on the resources page, you can see all the FPGAs. There's a column that says FPGA total and a column that says FPGA free. You can see them as a resource with kubectl. You can describe the nodes and see how many are available, how many are allocated. And in your YAML, in your Kubernetes workflow, you can already just, as simple as one resource request, you can provision FPGAs. And a line as simple as this can attach the FPGA and have it show up in your Kubernetes pod. And then you can start working on the FPGA. And when you request it, it's solely for you. So it's not shared with other users. You're provisioning the entire FPGA. And we're just going to get down to a hands-on example to show you how easy it is to provision FPGAs on Nautilus and how easy it is to run a very simple and straightforward example. So I'm assuming everybody got the link to the slides. This is the same repository. Does everybody have it all set? All right. We're gonna walk through it together. So this is the interesting part. We've been talking a lot in theory about what FPGAs are, what they're capable of. Now we're gonna go step by step to see, to each one of us, we can see how we can provision FPGAs and we can run applications, and we're not gonna write our own C++ application to see how they work, because it might be tedious to write the C++ into the tutorial and run it, but we're gonna walk through an example and see how it works. So you can see here, first step is to sign up for Coder. So Coder is on coder.nrp-nautilus.io, and it's linked in the markdown, so you can see here. Here's the link, and here's the link in our documentation for Coder. Once you click on the link, you can see, so this is what my page looks like. This is how I can sign up for Coder. And I'm assuming everybody here has institutional credentials and institutional emails. They can just click on OpenID Connect. Just gonna do mine. And log in. Whether you have an account, you'll be able to directly log in. If you don't have an account will be created for you in the process here. And I'm just gonna walk you through Coder a little bit. So this is what Coder looks like. And as you can see, to explain a little bit what it is essentially a web service. So it is a website that every user on Nautilus that has institutional credentials can just go on, create an account, log in, and you'll see something similar to this. So Coder allows us to do almost everything that we can do in Kubernetes without having to learn Kubernetes and know how to write YAML and request resources. So normally we request pods, and pods run Docker containers. They're very similar to VMs. They're the single unit that we work on. Here, pods are called workspaces. And workspaces are launched from already existing templates. So this is what my templates look like. You can see on Coder, I have many options. For example, I have the universal image. If I click on the universal image and click create workspace, you can see I can name my workspace. I can specify how much CPU and memory it has. So these parameters, these options are specific for the universal image. So if I pick my CPU options, my memory options, what it's gonna do is that it's gonna start a pod for me, and start one real quick. It's gonna start a pod for me with the resources that I requested, and it's gonna request persistent storage onto my home folder. So the user inside the pod will have persistent storage. Whatever files I write to it, they'll exist there between shutting down between.
Recommended like number of like CPUs or RAM when using like Vivado?
Yeah. So it's always good to monitor how much you're using.
Sure.
If you're using Vivado and Virus, if you're developing, you're writing simulations, you're doing synthesis, odds are you're gonna require a lot of memory. So just purely for the example we're gonna do here, the simplest example, the Hello World example, that one we monitored, it peaked at 30 gigabytes of RAM.
30?
Yeah.
Oh.
So 30 gigabytes of RAM. Let's say we're all here landing on the FPGA nodes to carry out our experiments. If we're all using the FPGA nodes and requesting 30 gigs of RAM each, odds are we're not gonna have enough memory for everybody. So it is a good best practice to have sort of split workflows, development on one pod and deployment on one, just so you have this distinction, and just so you're not, for example, hogging and requesting the FPGA while synthesis, even in the simplest Hello World example, synthesis might take up to an hour.
Right.
If you're running more intricate workflows, if you're running from a higher level, if you're running something that needs a lot of optimization in the compilation process, it might take up to Like in our experience, it have taken over 10 hours for some applications.
Thank you.
Of course. So once we start working on the example, make sure to request at least 32 gigabytes of RAM. Otherwise, your pod might crash. And if it runs out of memory, it'll crash. You'll have to restart from not from scratch because you have persistent storage, but you have to restart the experiment. So this is what it looks like after I provision a workspace on Coder. One of the main advantages of using Coder is VS Code Desktop. So Coder has a desktop plugin. You can just click this button, it'll start VS Code on your desktop and connect your workspace to it. So whatever you have on it, you can run it, you can open a terminal in it, you can access the files, persistent storage, and do whatever you want.
You mean desktop on my machine, like using a remote connection, or do you mean like open it as like run VS Code directly on in the?
No, it'll launch on your machine.
Oh, okay.
So the folks that wrote Coder actually wrote a VS Code extension that does it for you. For example, I'm using the universal image in this example. The universal image, it's a Microsoft provided image. It's freely available. It provides a lot of programming tools and whatnot. It doesn't have a remote desktop already provided with it, like no VNC or Selkies or other setups.
That's where you want VS Code.
Yeah, so I can just see it says like on a first instance, it says install the extension. After you click this is VS Code on my computer.
Yeah. Right, perfect. Thanks.
And it also has Code Server. So Code Server, for those of you who don't know what it is, it's VS Code that is running on a port. It's a web service. If I click this one, it also opens VS Code from the pod itself. I don't have to have VS Code on my instance. And also one thing is terminal in a browser window. Click terminal, and I'm inside my workspace. This is the workspace I started. I don't have to go through more steps. I don't have to configure SSH on the pod and connect my actual desktop to the pod, actual laptop or OS, whatever I have locally. I don't have to connect it to the pod. I can just start my terminal browser, my terminal in a browser. And of course, Coder also has a CLI. You can install it on your computer. It allows you to see SSH and manage your workspaces, do whatever you want, but through a CLI. And the main incentive that makes us want to use Coder and want to push for users to use Coder more and more is that Coder in your settings, if you go onto your settings, you'll see an SSH key that is specifically for you. And that SSH key is private and is loaded onto every single workspace you start. So let's say take that SSH key, I put it on my personal GitLab. Now, whatever Coder instance I start, I can just push my code. And then that makes interactive development much easier, much more straightforward. And like we said, this workspace is essentially just a pod that has persistent storage, and we have many templates. The one we're going to be using here, the one we're interested in for the sake of the tutorial, is the U55C FPGA Vitis workflow. So this one has all the parameters we need to get started. So yeah. So U55C is the model of the Xilinx Alveo FPGAs we have. Let me name my workspace. So it has a picker for the number of FPGAs. For the sake of demonstration, just because I'm going to require a lot of memory, I'm going to go with no FPGA. I would recommend that many of you also try no FPGA just because the synthesis process, which we're going to try to attempt, requires a high amount of memory. And like we said, we only have 14 nodes with FPGAs on them. So if it's 32 gigs per experiment, we might run out. And this is the picker. So when I pick an FPGA, it's automatically going to land on a node that has an FPGA on it. If I pick no FPGA, it might land anywhere.
So I can use one of these Kubernetes pods that has all the development tools that doesn't have an FPGA, and it won't be allocated on the one of those nodes. It will allocate somewhere else.
Yeah.
On node or readily.
Yeah. So the way it works is that we have storage pools, we have self-storage pools, we have all the Vivado and Vitus and all of these Xilinx tools, we have them on a ready available volume. And when you request a workspace, regardless of where that workspace geographically is on the cluster, that volume, that PVC gets attached to your pod. So you can see them natively as if they are mounted on your pod, as if they are on your pod in /tools/Xilinx, and they'll be shared among everybody, and of course they'll be read only, so no one will be able to delete files for others and kind of wreck it. But if you request FPGAs, you'll be on an FPGA node, but you don't necessarily have to be on an FPGA node for the software stack to work. So the software stack is not dependent on the node. You can land wherever and you'll have all the software things you need, which are the software stack. The other component is the Xilinx runtime tool, which is called XRT. It's needed to talk to the cards. It's needed to in some workflows program the card. It comes preloaded with the Docker image that comes in using this template. And the last component is a license server. So many IPs in writing FPGA programs, a lot of the things you might use in your application, they might be licensed with a paid license. This paid license is available to academic institutes from Xilinx. We have a license server already set up. So Coder runs in the Kubernetes hierarchy. Coder has a namespace. The namespace is called Coder. All those workspaces that we provision, they're running in the Coder namespace. And that namespace has the license server inside of it. And it's already programmed onto the pods. So it's programmed in the environment variables that the license server is running as a Kubernetes service, point to that license server. So when you start the instance, you'll be able to see the licenses already preloaded. So if you have anything that requires a paid license, that is freely available when you use this template. So like you see, you only need the parameters for memory. I'm gonna go with 8 cores and no FPGAs and create. And this does it all in the background for me. Now, another thing to mention here is that by default, when you start a workspace, it defaults to 5 GB of persistent storage. That is, of course, modifiable from our end. So if you ever require more storage for your applications, you can always request more and we can expand it. For example, one of the templates is the CUDA PyTorch one. I doubt 5 GB will be enough to run any applications there. For some FPGAs, you might also require storage. And now we're just going to wait on it. It's doing it all in the background. First step is it creates the PVC, the persistent volume claim, and the volume with it. And it attaches that and the Xilinx tools onto my pod and then pulls the image. It might take some time. If this step takes some time when you're trying Coder on your own, don't be alarmed. It's in most cases, the bottleneck here is the time it takes to pull the image from our GitLab repository, the Docker image. So the Xilinx image, it's preloaded with a lot of tools. It has a desktop environment, so you have a GUI because Vivado and Virus and many of the tools, you don't want to write scripts to automate what you're doing in most cases. You want to use the GUI because it's simpler and more straightforward. So it comes preloaded with a desktop environment, comes preloaded with all the dependencies, all the tools. Basically, it's pulling a fat version of Ubuntu that comes preloaded with everything you're going to need. So it might take a while to load. But once it's loaded, you'll have everything you want. And while it loads, one thing I'm going to mention here is this is more related to Coder than FPGAs, is that where is it? We have also deployed Sulkies on Coder. So Sulkies allows you to have a remote desktop environment inside of a browser window with audio. And it also provides GPU accelerated streaming. So it's blazing fast, very smooth, and has audio capabilities. We're still trying to test it out and phase it out, but basically what we're going to phase out on Coder, we're going to phase out all of our Anovi and C desktop environments and replace them with Sulkies because it's unbelievably smoother. Even you don't have to use GPU acceleration, even using CPUs. It still supports audio and is blazing fast.
The audio configuration is easier and more straightforward than EMC.
Yeah, because the folks that wrote it, basically they have the Xilinx GStreamer application. It's programmed to sort of provide the pipeline for everything. So you install the client, even if you start a pod, let's say it's a matter of 5 lines and you're running Xilinx GStreamer on it with the audio working, everything working. And the web page interface, you have a right pane that has all the options. You can tweak like bit rate and frames per second. You can tweak the audio and video to your liking. And when it comes to graphics heavy applications, GPU acceleration comes in very handy. And we also added it on Jupyter also. So Jupyter Hub West, we also have sulkies, but you'll see if you go on, it says experimental just because we want more people to test it, but see if there's any kinks, just iron them out. And but yeah, whether you're running no VNC or sulkies or whatever desktop environment, remote desktop you're using, it runs privately, so no one else on the cluster can access it. Even it's set up that way. It can be disabled. Even from it can be disabled, but it's set up as that way as a parameter. So even for us as administrators from our side, if there's something going on from your no VNC instance to give you more privacy, we can't access it. So you can see there's a button that says no VNC desktop. And for sulkies, it's also as simple as that. It has a button, you can click it and it'll run. There's all sorts of apps and extensions that could be added as well. Some templates have Jupyter notebooks and Jupyter Lab running on top of them. Also click a button, you have it up and running. So this is no VNC. For those of you not familiar with it, you have a left pane here. You can see clipboard and other options. All right, so this is our instance. Just gonna open a terminal to show you around. So you can see here under /tools, /Xilinx. So this is where our tools reside. And like we mentioned, this is one PVC that is being mounted for everybody. You can see we have multiple versionings of the tools. For example, under Vitus, we have 22.2. One thing to mention here, in a lot of the cases, a lot of the applications you're running, you might be running a specific version for your applications. In that case, if you want a different version than what we have added, all you have to do is just go on Element, ask us to add it, and we'll happily add it. The reason we don't have all versions available is not to make one big massive PVC that is slow for everybody. But whatever application you have, you want us to add it, we're more than happy to. Of course, you don't even have to. All we're doing on Coder, you can do it inside your own namespace. You can start pods, add PVCs, install the tools, run your own images, but we're trying to provide a pipeline that provides everything for you so you don't have to reinvent the wheel. The other thing to mention here is XRT. So it's under /opt/Xilinx/XRT. Normally with the Xilinx tools, the way you load them, so if I run Vivado, it's not gonna run. This is one important thing, and a lot of users forget to do this step, and it's always needed for things to work well, is that you need to source a bash environment to be able to launch all the executables and point to the right libraries. So if I want to launch Vivado, I have to go source tools, Xilinx, Vivado, and then the version I want, let's say 22.2. The ones we have are 20.1, 22.2, and 23.1. And we're adding 24.1. We just need to test it a little bit to make sure our workflows work with it. And then you go to settings 64.sh. After you source this file, you can run Vivado. And of course, you can have one terminal load up one version of Vivado, another terminal load up another version of Vivado. Sometimes, if I try to launch this, sometimes in some Workflows, it might crash on some dependency. It's just because when you're running multiple environments, multiple workflows, sometimes the dependencies sort of clash. So we try to heavy light on the dependencies as much as we can so they don't collide with each other. But on the other hand, to have everything running, you need to have all sorts of tools. And now Vivado is a very heavy piece of software. So for those of you who are not familiar with it, it'll take a while to load. So I'm just gonna leave it running in the background. So far what we talked about is what FPGAs are. What we're gonna show you is the point of the hands-on example is to show you a hello world example that is written in C++. Now the way it works is that hello world example is then taken by another tool. So there's Vivado and there's Vitis. It's taken by Vitis and it's being compiled or synthesized onto the Verilog and they're on bitstream that we want to load on the FPGA. And at every single step, there are simulations. There are simulations and emulations. You can run what program you're writing before compiling, because compiling or synthesis, like we said, takes in the order of hours. So if you don't want to change one line, wait an hour and then run it again. In most cases, your workflow is going to be simulation, change, simulation, change, simulation, change. Once you see that it's ready, simulations are very accurate. Even their clocks, frequencies, it's the order of nanoseconds, and you can see it in the Vivado GUI if you want to dive deep more into FPGA design. And it is very accurate to what is actually going to happen on the hardware when you run the compiled bitstream. And while this loads, I'm just going to walk you through the tutorial. So here we go. So like we said here, if you follow the steps, we said use the U55C FPGA Vitis workflow template. I hope you all requested adequate memory so you can follow the examples. First thing is to install libboost. Libboost is a dependency for Vitis to work, but it's one of these instances where one dependency might clash with the other. That's why we don't load it by default, because it might crash some other setups, and then missing a dependency, you know how to figure out what dependency you're missing and install it. But having something crash because of a dependency, it's very hard to know what is causing the crash. So if I run apt update, like you can see here, we have the command sudo apt-get update, and then install. I'm gonna do this as while Vivado runs. Libboost -dev -all. Like we said, if you're writing, sorry, I have a typo somewhere. Oh, sorry, -all -dev. Sorry. Like we said, if you're running Vitis, especially with the HLS applications, it's always good that you install it. And just gonna wait on it to install. See, the next step is to clone the exact same repository that where we have the notebook in. We have the steps in. And no VNC, if you want the clipboard, it's right here on the left pane. And just paste whatever I want. So this is the clone command. I can paste it here and then paste it inside of my desktop. Now I've cloned my repository. We're just gonna go through the steps while Vivado starts. Sometimes if it takes a while and crashes, don't be alarmed. If in some circumstances the FPVCs are slow, things might crash and time out. But in most cases, just don't be alarmed. For those of you who are not very active users on Nautilus, we're always available through our matrix chat. It's referenced in our documents. For those of you who don't know where our documents are, it's just docs.nrp.ai. And if you know a different link like docs.nationalresearchplatform.org, it's the same documentation. And you can see everything here. Everything we're talking about today is provided in the documentation. So how to use Coder, how to provision FPGAs, how to provision FPGAs on Coder, and all of what we're mentioning referenced in the documentation, as well as how to contact us for any sort of support. Because dealing with FPGAs, it might be a little bit tricky. So if at any point you might require any assistance with anything, we're always more than happy to help. And now Vivado has start GUI now, so it should be showing the splash screen soon. And I'm just gonna cd onto the repository. You can see here there's a folder called directory called Hello World. So this is where our example is. And Hello World, it's sort of a boilerplate, sort of a template, sort of a skeleton. Oh, sorry, let me plug it in real quick. So if you're planning on writing your own C++ HLS application, you can take the Hello World example and go off from there and chain. I'm sorry. Here we go. And essentially all you have to do is change the C++ code and everything will fall into place. Because like you see here, there's plenty of files here like xrt.ini. You have the details file, description, JSON. You don't have to go through all of these details and understand what's inside of these files and analyze them, especially the make files, to understand how everything works. This is the official Xilinx Hello World example. It's provided as a template, so you can take it and start by modifying the actual code of the program you're running, which is inside source. So SRC, if you cd into it, so you can see host.cpp and vadd.cpp, which is short for vector addition, which is what this application is doing. So the way this application works, the way most HLS applications work is that we're writing C++ program. This program runs on the CPU. It runs on the host. It runs on top of the kernel. And then this program calls a library that calls the program that we loaded onto the FPGA. So we have our host.cpp. This is one C++ program. And the way to think about it is that we have the FPGA application. So vector addition vadd.cpp. This is the FPGA application. And you can see here we have the splash screen for Vivado. The FPGA application that gets compiled into its FPGA specific executable. That gets loaded onto the FPGA, and this one references it. So the paradigm of my workflow is going to be, I have my application that is running on my computer, just normal programming, and I have the tasks that I want to accelerate. Those tasks I take out of this C++ program, put them onto this one, write it so it's FPGA compliant, and then have this one reference this one. Not reference it as a C++ file, but more like reference it as the FPGA. And we're gonna show you here what I mean. Does it have it? Oh, let me show you in the browser so it's easier to read. So this is our host application. You can see here it's importing the XRT stuff. This is what talks to the FPGAs. If we scroll down a little bit, you can see here. So this device index is getting the device ID. Then we're auto device here is selecting the device that I have. So if I'm on a pod with multiple FPGAs, it's gonna pick one of them. And we're specifying in our make file that we have a U55C. So if I have multiple cards on my pod, let's say I provision multiple ones, it's gonna pick one of them from listing all of them and picking one. And then this device.load XCL bin. So XCL bin is the artifact. It's the result of compiling the program with Vitis, which is what we're gonna do. This gets loaded onto the FPGA. And just go back and see if all right, we're still waiting on Vivado. Here's the splash screen if you want to look at it. Like we mentioned, it's a very big piece of software, so it might take a while to load. We're just gonna walk through the steps while it loads up to show you the GUI real quick. So after you've cloned the repository, like we said, you have to source the bash files to get all the environment set up to run Vitis and run everything, XRT and everything. So to be able to run the experiment, you have to source /tools, Xilinx, Vitis 2022.2, and then settings 64.sh. Similarly, I'm not going to do it because it's going to make everything slower. If I type Vitis in this one, it's going to start Vitis, but it's going to make everything slow. And if you want to experiment with simply pure compiling C++ for FPGAs onto XCL bin, you can simply run V++, which is the Vitis compiler that takes C++ HLS code and compiles it into lower level Verilog and synthesize it into bit streams. And we also need to source the Xilinx runtime. So in sourcing, XRT has multiple tools to interact with the cards. See, here's its output. Once you've sourced it, you can run its own commands like XP management. So I'm going to show you XP management examine. Shows me all the cards on my OS. So right now I provisioned 0 FPGAs. That's why you can see here it says 0 devices found. But if I requested one, it's going to show one. If I go on the host that has multiple ones, it's going to show all of them. And from here, I can hot reset the device. I can flash the device. I can program it with a new shell. And I can see all sorts of stats about the device and health information. Now that I've loaded sourced both files, if you scroll down here, you see into the Hello World directory. You can see here, I have 3 options. So we have software emulation, hardware emulation, and hardware build. So this is the official Xilinx example. They have deprecated software emulation. And the reason is beyond me. Honestly, I have no idea why they deprecated it. But since we're running a 22.2 version of Vitis, you can still run the software emulation. The make file is supposed to scream at you because the make file is recent. It's pulled from a recent example. But if you go on to the Xilinx repository, let me show you. So this is Google. So Xilinx. With this hello world. Sorry. So if you go on here, you can see the Vitis tutorials. And you can see they list more here about the hello world example. So they do provide more documentation about the hello world example. But the thing to notice here is that software emulation, if you try to run it, let me show you what I mean. So this is the command. The command is make, since it's in the make file, and make all, and we're setting the target to SW_EMU. Let me make it large. Sorry. Here we go. So SW_EMU is what runs the software emulation. HW runs the hardware emulation. And HW is what actually compiles it to run on the hardware. So software emulations, they're very accurate. They run in inside of Vitis. Hardware emulations, the difference here is that software emulations is designed to run a simple simulation that is taking the source code and transforming it into a simpler design that can be run by software that simulates the behavior. But hardware emulation is more intricate. It takes into consideration things like clock cycles and frequencies. When you run the hardware emulation, it's designed not to simulate the behavior of the software, so it's run to simulate the behavior of the hardware. So it's not, software is sort of a rig, it's sort of a debugger, it's a sanity check, but hardware emulation is very accurate to the nanosecond. It is what's going to happen if you run the application on the FPGA itself. And I'm just going to copy the software emulation part. Here we go. Oh, sorry. I'm in the wrong directory. You should be in hello world. If we attempt to run this, you can see it's screaming at us. That screaming message is artificial. It's from the repository that has the example. If you pull at an earlier commit, you can very straightforward run the software emulation, but we're going to go straight to the hardware emulation. And you can see it here. Did we go wrong? Sorry, let's go back. And paste it. Yeah. Huh. Okay, we're running into some error. Let's see what's going on. Okay. Just real quick, clean up and reclone. So there we go. Huh. Okay, we are running into issues. I'm not gonna hold up your time. We'll figure out what's going on. But just to show you what the expectation is when you, oh, sorry, here we go. No, sorry, my bad. Yeah, so we have some issues. You have to iron out, see what's going on, but the example should be fully functional. It should work. I don't know why my setup is not working. Oh, you're having the same issue? Oh, then I might be missing a file in the repository or something. I'll make sure to follow up with with the right example and update the repository.
Yeah, I think people are getting similar.
Oh. So. Oh. So this is the repository for the examples. I'm just gonna add it to this, put it on the screen. So if you want to clone it directly from here, you can see it's github.com/xilinx/vitis_excel_examples. Are you facing issues?
Yeah, you need to source. But it's not livable.
Yeah. Am I sourcing? Let's run through it together. Let's run through it together. Okay, so Vivado started, just so you can look at the GUI while we have it here. This is what Vivado looks like. It's a GUI. I'm just going to walk you through real quick. You can start a project here. You can select the FPGA model you're working with. You can select the sort of project you want to work with. And this Vivado is already, and Vitis, they're already linked to the license server. I'm just going to go through. So we cloned the example. We CD into Vitis Excel examples and hello world. Now let's attempt to run it. Okay, here we go. Now it's running. So something might be corrupted from our repository. If you try to pull the repository with the, so if you pull github.com/Vitis/Xilinx/Vitis_Excel. Have you tried pulling it? So as long as you can see, you see here, once we ran it, you can see G++. Is it all set now?
Just like you were saying, the example folder from Vitis is working.
Yeah. If you clone it, see where, let me scroll up. It might have been corrupted and stuff. I apologize for that, but have you tried? Is everybody? Are you facing issues with?
But I can reclone the original to do it again.
I'm trying to figure out what might be missing.
Oh, so you're trying to.
I mean, yeah,
You can try.
why not? We'll go.
If you see here, so G++ runs first to compile the host part, and then V++ runs to compile the FPGA part. One thing here, when we say kernel, we mean the kernel is the processing kernel that is being, it's logically on the FPGA. So kernel in this context means the FPGA program. And host means the CPU program that is running the program that interacts with the user. So host.cpp, it's my own program. I can run it I can write it to take user input. I can write it.
Did you source the Vitis script or the Vivado script for this?
This one will like.
Vitis.
Okay. No, but you know, those are the bash script that you run in order to settle.
Yeah. So I sourced Vitis for this one. If I remember correctly, if you source the Vivado one, you might the Vivado one is missing V++. Realistically, if you're running the same version, you can source both without running into conflicts. But if there's multiple versions, you might run into conflicts. Here I'm running make hardware. This stuff might take a while, so we don't have to wait on the results, but you can keep it running on your computers. You're gonna have the results. If you see on the README. So after you source and go onto the repository and compile. So you can see here, you have xcl_emulation_mode. This environment variable is how you're telling it how to run it based on how you compiled it. And you can see here, this is our compiled program. Hello world_xrt, so Xilinx runtime. If I pass, I need to pass the build directories where it's built, SW underscore MU is for software emulation, hardware underscore HW underscore MU is for hardware emulation, and HW is for actual hardware. You can see the XCL bin here. So based on how you pass this and having the correct XCL bin that corresponds to it is how you're going to get the results. So the results in all three cases should be that the test passes. And how the test passes is in the host.cpp. So if we look here, this is source. So this is for the most part. This is plain CPU, normal C++. It's just using the XRT stuff and selecting the device and loading the XCL bin. And this is the XRT kernel we're talking about. So the kernel is the software we're loading. So we mean the FPGA kernel. So the FPGA is C++ program. VAD is what we're calling it, which is vector addition. We'll see here. So this is buffer 0 and buffer 1 and buffer out. So those are the buffers going into the FPGA and out of the FPGA for input and output. So you can see here. So we're taking from the BO map. This is SDSC out. This is just for us normal CPU C++ application printing for users. Sync. So this syncs the buffer onto the FPGA. And if you go on to the other part, which is the vector addition here. You can see here they have a visual of how input vector and then in one stream and two stream, in one stream and into stream and output stream. You can see here they're inside, they're coming from the buffers. And pragmas are in the simplest way, they're directives. They're sort of giving commands to the FPGA. Pragmas, this is where you have to learn how to actually write programs for the FPGAs. But in simple programs, whatever you write for CPU, in simple, not very complex scenarios, what you write for CPU can run on FPGA without change. So your CPU C++ code can run in a lot of cases, not all of them, but it's not going to be it's not going to be optimized at all. You have to learn how to write C++ code for FPGAs to make use of things like parallelism and concurrency. So you get your results fast. So this is where the FPGA power in C++ comes in, is because you want to do things concurrently. And I'm not going to go through all the nitty-gritty details of the C++, but basically it's taking in both buffers, adding the two vectors. So it's simple vector addition, and then returning the result to the host application on the other end. Then the host application, what it does is just all it does is it does the same operation on the CPU and compares the results. So you can see here it throws to the user. Value read back does not match reference. So how it verifies that what is running is correct is that it runs the same stuff on CPU and verifies the results. In FPGA design, in 99% of the cases, what you're gonna get is not an error. What you're gonna get is the wrong output. So that is one caveat, one thing that is not very likable in programming FPGAs. But with practice, you can learn how to use the pragmas. You can learn how to use the parallelism and write FPGA applications. See here. So, sorry. So the pragmas, they're directives to the FPGA. We have a library that the XRT library that defines the C++ methodology for the FPGAs. The pragmas that you can use with the FPGAs, most of them, what each one does and how to use each one is in the Xilinx documentation. But you can think of it as like programming embedded hardware. In the same fashion, pragma is sort of just giving it sort of an instruction. It's closer to assembly instruction. Yeah, and then, like I said, in the Xilinx documentation, if you look at the Vitus HOS documentation, They do provide you with some fragments what each one does, and if there's anything models. So for example, the U55Cs have DDR memory and HDR memory. So some of the other model cards don't have HDR, just have DDR memory. So they might have different drivers.
Hi everyone, let's continue our tutorial on FPGA applications on Nautilus. And this section, we are going to discuss scientific applications in the physics domain. My name is Elham. I'm a computational data science researcher here at San Diego Supercomputer Center. So first on this slide, we have the setup instructions. I want you to go to the GitHub page, which is the link is written on the slide, and you can also scan this QR code and go to the page. So this GitHub is the same GitHub organization that we used for the previous part of the tutorial, NRP Nautilus, and then inside that there is a project directory called NRP-HLS for ML, and I'll just show you quickly. So this is the GitHub repository, and if you go to the GitHub repository, we also have instructions for the whole tutorial as well as the link to the slides. So I want you to follow the instructions for this part of the tutorial. I want to highlight that we are not going to use the coder environment that we have been using for the previous part of the tutorial. So for this part, we are going to use Jupyter Hub, and this is the Jupyter Hub link. So if you are on the GitHub page, you should be able to click that link. And if you still are not there in the GitHub page yet, the Jupyter Hub link is 6nrp.nrp-nautilus.io. So you can just kind of type that on your browser and go there. But I would suggest you to go to the GitHub repository if you haven't still been there. So if you go to the Jupyter Hub, you will see this page. And let me log out first. So if you go to the Jupyter Hub, you'll see this page. And that page will show you like sign in with CI logon. So I would just ask you to click the CI logon button, and then I will choose University of California, San Diego. So you should choose your university name or your organization name and select log on. That will take you to your organization login portal. And then with the credentials, you should be able to log in to the Jupyter Hub portal. Once you go to the Jupyter Hub portal, you'll see a page like this. So at the beginning, you'll see like, the server options where it asks you to select a bunch of different config options. And then there's a list of images that you can select. And then finally you can start. So our Jupyter Hub, our GitHub notebook also has these instructions written as well. So we already followed the step one. We went to this Jupyter Hub link, logged in, and the second step is start the Jupyter instance. So in order to start, you should be selecting the Jupyter image, which is the name 6nrp tutorial, and then the other server options like CPU is a 4-core, RAM 32 GB, and no GPU. So let's do that. These are also, like, by the way, the default options. So if you don't change anything, you should be good to go. The region, you just keep it as it is. So it could be in any region. And then the GPU 0, core 4, and RAM 32 GB, GPU type any general, because we're not asking for any GPU anyways. And this is the image that you need for this tutorial, 6nrp tutorial, FPGA, and then I hit start. So all of you should be doing this at the moment. We really want to get started with the Jupyter Notebook part and download our code there, and then I'll go back to my slides and continue talking. So I'll give you a few moments to start your Jupyter Hub, and then I'll show you what to do with the next steps, and then I'll come back to the slides and continue. Okay, so I hope most of you already have your Jupyter Hub instance running. So if your Jupyter Hub instance starts without any issue, you should be seeing a page like this. It is a launcher page, and then there's notebook options, console, and then there's a few other options. So let's continue with our instructions. So we already did step 2. We should be doing now the step 3. So it says like open the terminal from the Jupyter Hub launcher, and then we have to do a few things there on the terminal. So this is the terminal at the very end of this launcher pad. So let's click the terminal. So it'll open the terminal on this environment. So the first thing we want to do in step 4 is we want to make our environment available for the Jupyter notebook as a kernel, because we are going to use Jupyter Notebook for our tutorial, for this part of the tutorial. So the first command that you need to run, it's written on the GitHub README file. So let's just copy that line and paste it here on the terminal. So if you hit enter, so that says that installed kernel space HLS for ML inside this local shared Jupyter kernel folder. So essentially what we did is that we just created a kernel named HLS for ML, and I'll tell you why HLS for ML and what is HLS for ML and everything in the next few minutes. But we just took our environment. So for this environment, we're running a Docker image which has everything installed, and we're just taking that environment and making it and saving it as a kernel HLS for ML available through the Jupyter Hub notebook interface. So let's open the launcher again. So if you now open the launcher, you will see now there is an option for notebook called HLS for ML. You should just click there. So that will create an untitled notebook. But first, before continuing with that, let's also follow for the next step that says we should clone the Git repository. So this is the same Git repository where we have these instructions written in the README file. We have the available codes as well for the tutorial session. So let's clone those codes. So we'll just run it git clone and then git repository link. So it should clone the 6nrp-hls for ML git repository on this platform. Let me just close the untitled and delete it as well. Yeah, so we have the 6nrp-hls for ML, and inside that we have the 2 notebooks. So I want you to open both the notebooks and then let's continue with our next step. So the next 2 steps, like step 5 and step 6, describes the notebooks. We have the notebook 1 and notebook 2 describes each notebook. So you should probably look through that later on, because in this short amount of time, we are not going to go through too much details and explain each and every thing on the notebook and each and everything in terms of context of this notebook. But the first thing you should be doing, you have both the notebooks up, you should be just running the notebook 2, so the 02_hls_conversion.ipython notebook. You should be just running that notebook, the whole notebook. So I want you to hit this double play button. So if you just click that, it'll pop up this window. It'll ask you whether you want to restart the kernel and run all the cells. You just say restart. Yeah, and another thing to note that you should have your kernel to be HLS for ML. So make sure that you see your kernel that we just created a few minutes ago. It should show up. So we are using this HLS for ML kernel, which has all the Xilinx tools and necessary Python packages, everything installed. And this is what we are going to use for this part of the tutorial. So Okay, so let's continue with the slides now. So now that we have the Jupyter instance running, we have also executed the whole notebook too. Let's continue with our discussion here on the slides. So I want to reiterate about the FPGAs again. We have been talking about FPGAs, and previously Mohammed explained a bunch of different concepts and different computing units inside the board, and you also have done one example just before this session. So FPGAs are field programmable gate arrays. These are essentially reprogrammable integrated circuit. There are many different building blocks inside the FPGA, and we call them as resource. And I'll highlight a few of them for this part of this discussion. And originally, FPGAs were popular for prototyping ASICs, which are integrated circuits, the chips that you see in all sort of electronic devices. And even as you know, that once you make a chip, you can't really change it. It has to be programmed the way it has been designed. So FPGAs are a very great tool to kind of do your studies and optimize the design. So there are like the four building blocks, the four resource units inside the board that I'm going to highlight here: the multiplier unit, DSPs, lookup tables, or LUTs in short, flip-flops, and block RAMs. And there are many more, but these are the important ones that I'll highlight for this part of the discussion, and it'll come up in the next few slides as well. So FPGAs are very fast, used for very fast computing. They can execute or perform in a megahertz rate. So that's extremely fast. And as we kind of already understood, that traditionally FPGAs are coded with Verilog and VHDL, the hardware low-level hardware description languages. But that's very difficult, or I would say rather there is a steep learning curve to get to there, to learn Verilog and VHDL and start coding. So for software people like us who are more familiar coding in software programming, C, C++, and Python, it's not easy to get started. So that's why, like, thanks to all these HLS tools, the high-level synthesis tools, these tools take the C, C++ like code and then translate them to VHDL or Verilog, and through a HLS synthesis, and that's what we're gonna see later the example that from the physics side. So very quickly, I will highlight some of these building blocks that will also come up in our discussion as we go. So the DSPs, the digital signal processors, are the specialized unit for multiplication and arithmetic. And those are the ones we're going to talk a lot and highlight when we take our example from physics, which will be training a machine learning model and then implement that machine learning model on an FPGA so that we can execute that model very fast. So the DSPs are much more faster and efficient compared to the lookup tables, and we're going to see what lookup tables are. So lookup tables are logic cells, and these are also used to perform arbitrary functional operations or small bit width arithmetic operations like small multiplication, small addition, and it can also be used for small memories as well. The other other resource that we have on the board, and a lot of them are the flip-flops. And flip-flops register data in time and with the clock pulse. And if you're not familiar with the clock pulse and the FPGA how FPGA functions in general, I would say not to worry too much because I mean, we can't teach you everything in this short amount of time. So you can go back and read about them a little bit, but then just to keep in mind that flip-flops is another resource that is available, and and there are a lot of them on the board. And then last, the RAMs, the block RAMs are just the memory, and usually you use them when you have a larger memory because you can always use the flip-flops or the logic cells, the lookup tables for a small amount of memory. Okay, so with that, let's just see quickly again, like we have discussed about this, like how FPGA programming works. Mohammed highlighted that and showed you some examples just before this. But just to highlight again and just to put this picture clear in your head, we start with the C++ algorithm. So the code is written in C++ with some constraints and directives coming from this specific compiler. Depending on which tool you're using. If you're using some of the Xilinx FPGAs, you'll have Vitis and Vivado. So you'll have directives according to that. You have other options like from Intel or Mentor. So First step, the C++ code gets compiled and produces a VHDL and Verilog code. And then once you have this VHDL and Verilog code, that is kind of already the native way of coding your instructions for an FPGA. So you have to take that VHDL and Verilog code and then compile them again to produce the framework block that you will be implementing on the FPGA. So there are two set of compilations, and we'll see an example shortly to do the first few steps. So since we're going to talk about a neural network operations on the board, so I thought let's just highlight how we can do a neural network computation on an FPGA. So just to be very clear from the beginning, we are not going to train a neural network on an FPGA. So neural network has already been trained with CPUs or GPUs, and you have the trained neural network. So our task here is to take the neural network which has been already trained and implement this on the board and do the inference. That means trained network will just predict. So essentially, it will be used for any sort of real-time analysis or real-time data processing kind of application. So very quickly, if you have a feed-forward neural network with multiple layers, the kind of operations that you're looking at, like a simplified version has been written on this slide. So let's assume we have this XM vector, which is a column vector with m dimension. That's the output from the previous layer. So if you take the vector in the previous layer, which is xm minus 1, and you do an operations, this matrix multiplication operations, that's the W matrix, which takes the m minus 1 as dimensional vector to mth vector, and produces this xm vector. So we have this first multiplication operations. It's a matrix multiplied with a column vector. So it's a matrix multiplication, and then we have another column vector, bm, which does which gets added with this output of the multiplication. So we have a multiplication and then addition, and together we get a column vector. And then we have another functional call. So there's a m-dimensional function as well, which takes elements of this vector that's get produced after this multiplication and addition, and transforms them based on the function, whatever it is. And then finally, you get the XM. So there are a few different operations happening here, multiplication, addition, and there is a functional evaluation. So in your head, we just discussed that the building blocks and what are the major building blocks that we have, and what sort of operations that do, arithmetic. We talked about arithmetic. It can be done with DSPs or lookup tables. It's a functional call. So the first thing, this whole arithmetic part, the multiplication and addition, I think DSPs might be the best because we just highlighted those are the more efficient than lookup tables. So if you have enough DSPs on the board, you can choose to use all of them for doing these kind of operations. And then the second part, where we have this G of this vector, this can be done many different ways. If you have a very simple function, you can just use the flip-flop or some other sort of logic cells. You can use a lookup table where the function is already pre-computed and then stored in the form of table. Or you can also use a block RAM where a complicated function can be stored in the RAM and taking a larger memory. So this should give you naively some intuition, how a neural network kind of operations can be done on an FPGA circuit. So now with that kind of idea keep in mind, let's see the whole workflow. So in this tutorial, and in particularly in this application, we are going to talk about a tool called HLS for ML, which is high-level synthesis for machine learning. And this is a tool developed by scientists and computer engineers and machine learning experts and electrical engineers. This is largely from the academic scientific community to solve certain purposes. I'll highlight them as we go. So the first part is that, the machine learning examples that we always usually build, the algorithm and model building side, that usually happens at the Python-based tools like Keras, TensorFlow, or PyTorch, and a few other tools. So that model building part is always in Pythonic. So what HLS for ML does is takes that Python model after you optimize it and does the HLS conversion. So meaning the Python instruction of a model gets re-implemented again with a C++ like instruction. So you gets basically recoded in C++, and which is compatible with HLS and certain type of compilers of HLS. So that first step, the HLS conversion from Python to C and C++, and then you use the compiler to create this HLS project, which will compile your code and create this project, and you will have an opportunity to do a tuning. You can try tuning some of the resource usage and the latency throughput, like how fast you want to do, like what, keeping the application in your mind. You can do a few different optimizations there. And then once you have that, it creates the VHDL and Verilog code. We already mentioned that. The next step would be taking that VHDL and Verilog code and do the compilation for a specific hardware that you have, like either it could be an FPGA, it could be an ASIC. And the FPGA could come from a different companies, and you specifically target that and use their specific vendor compiler and produce your code to be loaded on an FPGA. And that part also can be done within HLS for ML, because HLS for ML has an interface which calls the compiler for you. So you don't really need to take your code and put it somewhere else again and run the compiler separately. It's all integrated. As long as you have a model which is in some specific Python format in popular machine learning formats, the rest of the things, converting to HLS, compiling them, producing a VHDL Verilog, compiling them again, producing bitstream to be loaded on FPGA, can be all done within HLS for ML. So this tool so HLS for ML is a software interface for implementing neural network on an FPGA. It supports many different common layers, like a deep neural network, like a dense layer, the convolution neural networks, so convolution operations, RNN, the recursive neural network architecture, graph neural network architecture, transformers, etc., and a few others. Everything is not mentioned here on this page. And it has also various different type of backends, and that means that the type of vendor tools that it can be compiled for, your code can be compiled for, there are various options. For this tutorial, we are going to stick to the Xilinx board. So we will be using Vitis, Vivado Vitis. It used to be Vivado, and then now the new tool is called Vitis. So we're going to use Vitis, a version from 2 years back. And the one thing also I want to highlight, there is an official HLS for ML tutorial repository, which is linked on this slide. And if you're curious and if you want to learn a lot more about them, you should go there and then practice the tutorials. It shows you a few different notebook style instructions, where it shows how to convert your model, having some of these architecture in it to a format that can be implemented on an FPGA. So for this tutorial, we're going to take some very early examples from this official tutorial and then practice here in the next few minutes. So the example case study is from physics, and this is particularly coming from particle physics application. And we are going to classify an object called jet. So what is jet? That will be very clear. I'll mention that in the next slide, but let's first understand what's the environment like what sort of particle physics collision we're talking about. So the kind of experiments we're talking about here, these are like bunch of protons are colliding. So it's like lots of protons together, they're colliding, and after their collision, they're producing all sort of new particles, and then those new particles are detected by detectors, and the detectors are put around the collision point, as you can see in the left-hand side here, and the atlas diagram, and it passes through the detector. And detector has multiple different layers to detect different properties of a particle that gets produced from this collision. And in the right-hand side, you see a CMS real event from 2016. And after the collision events, we actually have enormous number of particles created. So the environment is extremely messy, and it's very difficult to track particles and identify them efficiently. So we have to be really, really efficient at the very early data acquisition step. That's where the application comes. We use these FPGAs and this kind of particle physics colliders detectors to read out the data. And then do some filtering there on the right there on using the FPGAs. So that's the environment. You can keep it in your mind. And the jet is a collimated spray of particles. So once this collision happens, lots of particle gets produced, and then the spray of particle in the jets are some specific objects or specific response of an object, which are essentially the way you see it in the detector is a spray of particle. And depending on where the jet is getting produced or origin of the jet, it can have it can have different signature, meaning that it might look different, it might spread differently, it could have certain properties differently if you measure them. So we are going to use all sort of those properties to identify and classify them. So for this tutorial, we have a data set with 5 different types of these jets coming from 5 different various sources, and they have slightly different features and properties, and we're going to use all these properties to classify them. So it will be a 5-class classifier given the inputs, and then you're going to predict which class the jet the input belongs to. Here is an example of there are 3 different property. The 3 different variables are plotted here, and then all these 5 colors are 5 different types of jets, and this is from the training data set, and you can see that they indeed look different for different variables. First of all, the distribution itself is different, and then the different colors, lines of different colors, they also look different from each other for each variable. So we're going to use 16 of them, and the output would be 5 classes. So that's mostly it with the introduction part. And we're going to now again go back to our GitHub and then our Jupyter Hub notebook and follow the instructions there. So I hope by this time you all have your Jupyter Hub instance up and running, and you were able to follow the instructions with me and run your notebook, particularly the notebook 2, and particularly notebook 2. So I'll take a quick pause here and then and get started in a second. Okay, so let's go to the notebook, and then let's scroll down all the way to the end of the notebook and see if everything is printed. So it seems like at least my notebook has ran throughout. I hope your notebook is probably already completed, or if it's not completed yet, let it just run. So we'll come back to the notebook 1, which we haven't run it before. Let's just quickly go through this. The first notebook is training the network. So we just talked about this jet classification problem. So it's a 5-class classifier that we're going to train. So the first notebook is focused on getting the data set, visualizing the data set, defining the model, training the model, and saving the model, and check some performance, how good the model is performing. And then second part that we already just ran has the model loaded again. You load the data set, you load the model, and then you do the following steps of translating that model to HLS and then further compilation and all. So the first part of the notebook, since it's very, if you are not familiar with machine learning, we don't have adequate time to kind of go through each and every details here. So I'll not spend too much time here. But if you are interested, you should take your own time later on. Everything is available in the public repository, and practice it with your own time. And if you're already familiar in machine learning, it'll be very easy for you to understand. So I'll just quickly tell you what's happening here. So we are using a TensorFlow. We are using TensorFlow. So our model will be built with TensorFlow and Keras. And in this first cell, we're just loading a bunch of different libraries along with TensorFlow and Keras. And then we're getting the data set. The data set, first thing, we're printing the shape of the data set. So the data set has the X, which is the input. We're reading off the X and Y. So X is the input, which has this dimension, 16 columns. It's a tabular data set, so you can actually print them and then see. So tabular data set, it has 16 columns and it has 830K rows. So it's a huge data set for this. It's a simple enough problem, but it's a large data set, I would say. And it has 16 different columns with 16 different properties given a jet, and each row is corresponding to a jet. And given a jet with all the 16 feature variables, our task is to identify and tell which class it belongs to. And you can see the target values are shown in the form of letters like G, Q, T, W, Z, depending on which particle they originally came from. So the first, let's just plot the input variables. So all 16 of them has been plotted here. You can see, they all look slightly different from each other, but then also at the same time, in most of the variables here, we see differences between the different type of jets. So these are handpicked variables, which has been shown performing well in different studies. So we have been chosen that for this data set and for this problem here in this tutorial. So those are the inputs, and then the outputs, depending on how the jet, where the jet came from, their origin. These are the letters based on their origin, and like I said, they have different properties. So it is possible to identify them given all the 16 input features. Now, since it's a machine learning task and it's very difficult to do classification given all these letters, so first thing we're just converting them into numbers. So what we did here, we just used this preval functions to categorical from inbuilt scikit-learn and converted them into vectors. So we have 5 different classes, and each class is represented by a vector with 5 entities. It's called on one hot encoding as well. So one of them is 1, and then the rest of the entries will be 0. So if the class belongs to, let's say, for example, the Q is represented as 1 0 0 0. Then similarly, G is represented by 0 0 1 0 0. So something similar. So it's you have the 5 different possibilities, and all the 5 different options are each class represent to one particular type of vector. So depending on which class it belongs, it'll your target will be to achieve one of these vectors. But in reality, we're not going to get like exactly 1 and 0s and other sets, and the model is going to predict 5 different numbers, and then our task here will be to at least make sure that those 5 numbers add up to 1. So we want this model to predict the probability of a jet belonging to each of these classes. And then we'll finally decide, given looking at the highest value or something, we'll decide which class it actually belongs to. So here we are first doing this standardization. So we're just normalizing the data, like moving the mean and shifting the standard deviation. And then finally, the dataset has been stored. So you can notice the dataset has been this has already ran and stored in the GitHub already for you. So even if you don't run the first section, you already have all of them already stored in the GitHub repository for you. In fact, the model is already also stored in the model folder, model_1. But for completeness, I'm just quickly go through the model. So it's a dense neural network defined with Keras and TensorFlow. It has 3 dense hidden layer, 3 layers, so 64 input layer, and then 32 and 32 neurons in a hidden layer. And then it has an output layer with 5 units, because we want to predict 5 values. These are all probabilities, so they should sum up to 1. So that's why using a softmax activation function, which forces the network to output values which sums up all the 5 values should sum up to 1. That's hard reinforcement. And you can see that the number of parameters that we have in this model is around 4,300. And next we train the model. We trained the model and we saved it in an H5 format, and it's been already saved in model_1. So you can, that's why you can just run a notebook 2 without running notebook 1, because we just took the model, pre-trained model from notebook 1, which is kept in model_1 folder and loaded in the notebook 2. After the training, it's usually common to kind of check the performance, how the model is performing, is whether it's good enough or not. So first thing we do, we run some prediction given some test data set. So the data set which has not been seen by the model yet. It's a completely hold off, like a side data set kept aside during the training process. So this X test, which are the input having the same dimension, 16 columns, they go in and they predict the Y values for each of these jets. And then you can calculate the accuracy, which is roughly around 75%. So it's not really the best model, but it's also not too bad for this performance. So we have roughly 75% model accuracy, and then here this plot kind of shows you more granular information, like how accurately it's predicting the true levels. Like we are having a true level versus predicted data levels in the x-axis. There is another type of metric that we also check for this kind of classification task. It's called the ROC curve. And this ROC curve has x-axis of signal efficiency. So we want that value to be as high as possible. And then the background efficiency is the y-axis. And the background efficiency means how often a background is identified as a signal. So meaning, a jet which is not Q or not G is identified as a G or Q. So you want that value to be as low as possible. And you can see the lines are started from this corner to going to all the way to up to this corner. But this corner is not good because it predicts the signal efficiency is 1, so it means that it predicts all the signal jets as signal. But at the same time, the y-axis is also very close to 1, so that means that it also predicts all the backgrounds as signal. So everything is getting predicted as signal, so which is not very useful. So depending on your use cases, you might choose to stick to some sort of signal efficiency around 70 to 90%. And based on that, you decide whether this model performance is acceptable to you, or whether you want to train the model, continue training the model, change some parameters, and optimize a few things. So that's another choice you have. So I'll just pause here, and then we'll just continue and spend more time on the second part of the notebook, which is taking this model and building up the HLS and translating and compiling them. Okay, so let's continue with the second part. So we have already ran it, so I'm not going to run the cells while I'm talking, but nevertheless, I just keep highlighting the important concepts and important points that you should be paying attention to. So at the beginning, the first two cells, we are loading all the libraries that are necessary for this part of the tutorial. And then from the third cell, the section 1 is loading the dataset and loading the pretend model. So we loaded the dataset. The dataset were all saved in the NumPy format in py via the first notebook, and these are also available on the GitHub repository. And then we also load the model, which is from model _1, and the best model has been loaded, and we just checked for sanity whether the model is the right model that we loaded. The performance is around 35%. That's what we noticed from the previous training and the previous notebook. So everything seems to be right. So we have the test data set, we have the model, I have the prediction from the model stored in y_keras. Now the second part, the section 2, is where we take the tool called HLS for ML that we just described a few minutes back, and we will import the tool. So it has a Python interface, and we just import the tool in the Python environment here. And then the few things we have to do. So we have this model, the Keras TensorFlow model already stored. We have to take that model, we have to translate that model into HLS. So that's the first step. So in order to translate to HLS, HLS for ML tool gives you a few configuration options. So first we define the config file. So we start from the basic template that they have in the tool. We pass the model that the model we just trained and loaded here. The granularity says model in the quotation. That means it is going to set configurations or any sort of variable you are choosing to the whole model level. So everything inside the model, like all the layers and everything, will be applied to the same configuration that you'll be adding to this config file. And then another important aspect is the backend. So it's important to choose which backend you are using, because based on that, the compilation flow will be different. So in this case, since we are using the Xilinx FPGAs, the backend we have chosen is Vitis. So once we have the config defined, so it's a bare minimum you have to do. So we are already taking the config from the internal template from the HLS tool. Just bare minimum, we're passing the model, choosing a granularity, and choosing the backend. Then we're printing the printing the config file, and you see, like, it recognizes all the layers that we had inside our Keras model, all the dense layers and the ReLU, the activation functions, and then final softmax output. And then it also prints the configuration that we're choosing. So we chose the model levels. It just gives you the summary from the very top level, the model. So a few things to notice. We have a precision option here, and it says the default of the tool, which is fixed point numbers 16,6. So this is important to note. So when we trained our model in a Python tool, all the weights and other quantities stored are all stored in a floating point precision with 32 bits. Now, floating point precision in 32 bits, it's computationally not super efficient, particularly on a device like FPGAs where we don't have too many computational units, not like a CPU or GPU. It is important to make sure that we use the resources efficiently. So the first thing we do, we convert our floating point numbers to fixed point numbers, where the precisions are fixed, and we fix to certain bits that we can pre-decide. In this case, it picked up the default options because you haven't mentioned on the config, but you have the choice to mention it in the config by HLS4ML. So here it says 16,6. That means the second digit that you see, that's the integer part of it. So the integer part is been used to convert using 16 bits, using 6 bits. And the rest of the part, the fraction part, is using 10 bits. So you have this decimal numbers that we all have after the training gets converted into binary using 6 bits in the integer part, including the sign, and 10 bits, it uses 10 bits to convert the floating point, the fractional part of it. So if you have like 5.2, the 5 will be represented using 6 bits, including the sign, and then 10 bits will be used to represent this 0.2 part. And then a few other things are there, but then I'll just not highlight it for this tutorial, since we are not going to dive into too much details for this for the sake of time. So here, once we have this config defined, we printed it, and what we did next is that we defined a model called HLS model, which is an HLS converter. We're calling the HLS converter function, and we're using a specific converter function from Keras model because we have a Keras model. We are passing the model, passing the config file. We're setting the backend again. We are choosing the output repository and then the FPGA model here. And it creates a model, HLS_model. So essentially what we did at this through this line, we took our Python model through Keras and TensorFlow, converted it to an HLS model. So it takes all the Python instructions and convert them to equivalent HLS instructions, which is largely C, C++, and saves it inside this parameter called HLS_model, the variable called HLS_model. And then here in the cell number 7, we are plotting the model just to make sure that we have converted our model accurately. So you can see, we have the input layer, we have the dense layers inside with the 64, then 32, then 32, then we have the softmax output. And in every of these layers, each of these layers, you can see it's a fixed point 16,6. So the whole model got translated to HLS with this precision keeping in mind. So all the weights and everything in the parameters of the model has been adjusted a little bit to make sure those are all now 16,6 in a fixed point precision. So the HLS for our model, the next thing we are doing is that we are compiling the model. So it's an HLS compiler that gets used. So compiling the model, and then we will predict. So because we just took our Python model, defined the HLS, the first thing we should be doing, we should be like checking if this model at all performs equivalently, because they should be like comparatively pretty much the same, because we haven't done anything different other than just adjusting the weights and biases, all the numbers inside the model parameter. The model architecture and everything stays same. So that's what we're going to do now. So in 2.3, we are comparing the results. So we have the KRS model, that accuracy we are calculating, and we are also calculating the accuracy of this HLS model. And the outputs are also stored. The YHLS is the output of this model, and YKRS was the output of the KRS model that we have already saved in a few cells back. So we have been printing those accuracies, and you can see the accuracies look pretty similar. So they are both like very close to 75.8%. And also this ROC curve, where we are looking at the signal efficiency and background efficiency in the two axes. The two curves, two set of curves, they look pretty much on top of each other. Here, the solid line, which is the KRS plot, which you just saw in notebook 1, and the dotted line, which has been drawn for the same variable, same set of classes, with the same color, are for the HLS model, and they are very similar. There are some divergence in some places, but as we discussed, that for most of the practical applications, you might be choosing a signal efficiency above 70% or so. It doesn't really matter much, because at that regime, it's all they're all very same. They're all on top of each other, essentially. There's like literally no difference. So that kind of gives us the sanity check that, okay, our model is mostly working fine. So the next thing is to produce the VHDL and Verilog code. So for that, we need to do the full synthesize of the model, and this synthesize is called the HLS synthesize, because we have an HLS code at the moment. We have an HLS model. We have to synthesize this C++ code and produce the VHDL and Verilog. And that synthesize will be done with the Vitas HLS compiler, and it's already there in your environment. So the first thing we need to do, we need to just make sure that we add the compiler, the tools, the Xilinx tools, to our path, and then we run the compilation through the HLS for ML function. So HLS for ML has this HLS model build function, and that calls the Vivado HLS compilation in the back. So that's what you can see in the very top printout. It's the Vitas HLS or Vivado HLS. So in this case, we chose Vitas. So it's calling the Vitas HLS and starts the compilation. So the whole compilation takes a bit of time. So as it's already done, we can look at the results. Once it compiles, it produces the outputs and everything inside this model HLS for ML project. So you can quickly just go and see there's an HLS for ML project folder created. Inside that, there's a bunch of different folders. Firmware, you can go to the firmware and you can see like a bunch of different things there. You can go to the my project _ project, and you can see the solutions. That's the one you just built. The synthesis output will show you, you have the report, you have the Verilog code that's been created, and you also have the VHDL code that's been created from the model compilation that's already run at the beginning of the tutorial. So coming back here again to the top level folder. So we are printing the report. We are using this HLS for ML report function and reading the Vivado report from one of these folders and printing it here. So it tells you, when the compilation was done, the version of the tool, the solution folder, solution 1, we just saw that, and then the FPGA board target. And then it tells you a few different things. I just quickly want you to focus on the utilization part of it. So once it compiles, it also tells you how much resources on the board it's going to use if you run this model on the FPGA that you choose here. So we have chosen a Xilinx model board, which the U250. And that's a different board from the U55C that we have been we're having on the NRP cluster at the moment. So for this tutorial, I just chose a different one, but it doesn't matter. You can run this kind of model building also on U55C as well. It's just that the different board will have different amount of resources, so that you'll see here. So for example, like in this board, we have this is the available block section. So we have like almost like 12,000 DSPs. We have flip-flops, like millions of them, lookup tables, millions of them. And as you can see from the utilization, which is the report, the utilization is done by this model. It's using roughly 20% of the DSPs, our model. So it's using like roughly 1/5 of the board's DSPs by this small tiny model. And the lookup tables, flip-flops, is barely using any flip-flops and very little amount of lookup tables. So, depending on your application, which board you have, how much resources you have on the board, how fast you want to run, you have to kind of do an optimization in this compilation level to target certain resources. So you can go back and see, like, if this is 1/5 of DSPs on the board is too much, you can try, change some instructions in the compilation to make sure, the compiler uses more flip-flops and more lookup tables so that you can free up some of the DSPs and use them for something else. So that's sort of optimization you can do. And so once you have this VHDL and Verilog code created, you're happy with it, you can then take them and then run another set of compilation that could also be done using this HLS4ML tool. It has the Vivado synthesis option within the tool, HLS4ML tool as well. You have to just pass a different flag here, and it can run the Vivado synthesis for you, and it will invoke the Vivado compiler in the back, or Vitis compiler in the back. Okay, so that's mostly it. I think we are going to stop here for this part of the tutorial. The tutorial notebooks are available in public. You also have link to the GitHub repository of the official tutorial of HLS4ML, and you have our email. So if you have any questions, feel free to reach out, and we can discuss more in the future. So thanks, everyone.